Hey everyone, just want to give you a little bit of an overview of accuracy and precision, and then also go over the lab activity that we did a little bit ago, just so you can give a little bit of insight so that you know what to do when you do yours. So let's go over here. So we want to talk about um, two words that are pretty common in science and physics, but used interchangeably. They're really not interchangeable, and we'll figure out why. So when you think accuracy and you think precision, you sort of think, okay, we're gonna be on target, and we're gonna be pretty good, pretty consistent. Well, one of those words means one thing, and then the other one means like the second part of that definition. So when this was brought up in class, and you can think along and um, ponder it yourself, is, well, what is accuracy and what is precision? So when using accuracy and precision, we use them in terms of scientific measurements, but an easier way to think about it is by using, well, bullseyes and targets and stuff like that, because that's something that we can physically see and imagine more than how accurate and or precise data measurements are. So if you're thinking accuracy, we pretty much are going to use accuracy to describe how close your target is from your shot. So let me see if I can figure out my little drawing pad here. So bear with me. I'm still in red. Let's make that black. And with that, when we think accuracy, the best way to sort of put it into terms would be, that is, how close our how close the shot is from the target. So if you think of a bullseye here, an accurate shot would be straight down the middle. Now, well, the most accurate shot would be straight down the middle. Now, what does that mean for precision then? Well, for precision, that has to do with a lot of, sorry. It has to do with a lot of attempts. So I'm going to say used when, talking about many attempts. And both of which are used when talking about many attempts, but precision, in order to be precise, it definitely has to have more than one. Accuracy, you don't necessarily have to have more than one shot or measurement to be accurate. But when we're precise, we're going to be talking about many attempts. And more defined, I should say, is how close each attempt is to each other. So you can see that these terms, while they are similar, they don't mean the exact same thing. One is how close each attempt is to each other. The other is how close each attempt is to the target, to the designated area that we want it to be, to the measurement that we're looking for, the theoretical measurement. So these things don't have to happen at the same time. They are not interchangeable. So these things are definitely not interchangeable. You can be accurate and not precise. You can be precise but not accurate. So let's see what that looks like. Let's go up to a new page here and take it back to our target. So 1, 2, 3. Oops, that's a bad circle. Let's try that again. Well, that's as good as I'm going to get right now. So let's try to define a couple things. Let's say our target is, of course, the center. And let's say we're going to take five shots each. 1, 2, 3, 4, 5. So all 5 of those are on target, and they're also really close to each other. So the green ones are going to be described as both accurate and precise. What about where we have in the light blue? And we do our five attempts. 1, 2, 3, 4, 5. You can see that they're pretty close together, but they're also pretty far from where we want to be. So how are we going to describe that? So if you were thinking just precise, but not accurate, you would be correct, because these shots are close together, but definitely not close to the target. How about we'll go to this magenta, and we'll go 1, 2, 3, 4, 5. So what can we say about that? So with that, we know that they are close to the target, but not really close to each other. So these are going to be accurate, but not precise. And then finally, we have 2 options, and each of those options happens independently from another. Our last option, of course, is these brown ones, and the brown ones are neither accurate nor precise. So how do we measure accuracy and how do we measure precision? That's a good question. So how do we measure this? Well, you could make the argument that all of these things are relative, because in the grand scheme of things, like if you zoom out pretty much into outer space and take a look at this picture, you'd say that they're all pretty close together. But if you actually want to physically measure these things, a good way to do that would be using a meter stick or a measuring tape. So why would we use a meter stick? Well, take a look. If we want to measure accuracy, easiest thing to do would be, of course, measure how far something is to the center. So that's our center, and something pretty close to it. Then we can also use it to measure precision. Because if you take a look at it, these green dots, the ones that were precise, were really close to each other. So the distance between the furthest points is going to be pretty small compared to the ones that were non-accurate or precise, or even just the ones that were accurate but not precise. So this distance here is shorter than this distance. So using a meter stick, you can measure both accuracy and precision in this sense. So you can do both accuracy and precision. Oops. There's a big button on the stylus here. That's tough to not press, especially with my pen holding style. So you can measure both accuracy and precision in this sense with a meter stick. So that has to pretty much go along with our lab. And so what does our lab have to do? Well, our lab has to, well, it involves you going somewhere and actually doing something. Not going somewhere, but in class, what we did was we had our Friday fun day, and we, if you took a look in the lion's tail from this past Friday, we were able to take some golf balls and throw them into buckets, and then from there measure our precision and accuracy using a tape measure. So in the beginning, you can see, okay, this is what happened. And then on facts, I also shared with you this, as well as the table, the spreadsheet, and then the data for your classes respectively. So here's a little overview: low accuracy, high precision. You have low precision, low accuracy, low precision, high accuracy, and high precision, high accuracy. For now, I took the time to write the procedure in terms of what's going to be going on, but for your guys' classes, we're going to pretty much transition over at some point later in the semester to where you guys are going to be the ones making the procedure. So this is what's happening. You had the 5-gallon bucket. throwing it, recording the feet and inches respectively, and then it would be put into a Google Sheet pre-programmed by myself, and it'll compute the average distance for all 5 throws. The honors class will focus on standard deviation. And then a little bit of analysis. So what was the average bucket, average distance to the bucket? What is the spread between the furthest shots? How does your average distance compare to the rest of the class? How does your spread compare to the rest of the class? The honors class has a standard deviation question, and then the final analysis question is to pretty much take my definition, because I said that it's pretty arbitrary what accuracy and precision are, unless you're going into a percentage calculation, but we're not going to do that for this lab. So we're going to say accurate is no more than 6 feet away, and precise, so the distance between the two for the shots is going to be no more than 6 feet. So based on these definitions, we're accurate, precise, both, or neither, and how come. And then I added a challenge question in there. So we had a standard Olympic bullseye shown below, and competitors gain points depending on how precise and accurate. So what we did, and this is where your guys' labs are going to differ slightly, but not too much. So we're going to say that these 3 innermost rings are going to be the diameter of the bucket. And then each additional space is going to be half the diameter. So imagine you're starting at the center, going out to the edge of the third circle. That's going to be your radius of these ones. And then from here to the next spot, it's going to be another radius. So you have 1 radius going here. Then you have pretty much 2 radii going from the center out to this 7-8 border, 3 radii going to the 6-7 border, and so on and so forth. How this is going to differ for the virtual students is I have made this so that it can be adjusted to whatever equipment you have available to you. If you have 5 golf balls and a 5-gallon bucket, and you can just pace off 10 meters away and go throw them in the grass and see how well you do. If you don't, well, that's okay. You can use a wad of paper and a trash can, or don't draw on a floor, but mark a little circle on the floor and use pieces of paper there, or bean bags, or pretty much whatever you have available to you that you can use. So that is the lab. Of course, the virtual students analysis is going to be a little bit different, because you can't really compare your distance to the rest of the class. But if you want to, and I would highly suggest it, being able to take the data that I gave you, so you can't compare your distance, but you can say, okay, well, this person was better than this person. So it'll be a little bit off for the virtual students for you guys, but you don't really have to worry about if you're not doing this 1-for-1, you don't have to worry about questions 3 and 4. In facts, you'd be able to hit homework drop in the LMS, so you can attach whatever file that it is. And I'm going to try to keep this not going a little bit much longer. So honor students, I will make another video describing a little bit of standard deviation, how that relates to our lab. But other than that, I appreciate you guys watching, and I'll see you around.